Hello, welcome to video 31 in the lecture Advanced Mathematic Modeling. So we're investigating a correlated random walk, so where with a certain probability we repeat the last step, and with another probability we invert the last step. So this introduced a memory in the system, so it's the first random walk or stochastic process with a memory that we're investigating here. And so we started to calculate the autocovariance function, and so that we see that the memory of the system can be expressed in the expectation that the increment at a certain time correlates with the increment before, and we saw this here in this example. This autocovariance decays exponentially as a function of the time difference. And so in next video, in the following of this video, now we want to see what does this mean for the position of the walker. And so we have previously we have calculated what is the expected position of a walker depending on the moments of the expectations values, and this we can use now. Okay, so let's calculate this. We want to know now for the walker, so what is the expectation of our walker after n time steps? And look up in your script. So this was n times the expectation of the increments, but the increments are 0, so this means also on average the walker does not increase its position. And that's also what we saw here in these examples. I mean, for this q equal 1, where we had this persistent behavior, so either the walker was increasing in positive or negative direction, but on average the average position is still 0. Here anyhow, like for q 0.5, it's a random walk with non-biased, and for the anti-correlated, for q equals 0, the expectation of the walker stays around 0. Yeah? So that's clear. The expected value of the walker is 0. But now we need to know the scattering about this, so we need to know what's happening to the second moment of our walker. What's the second moment? Yeah? And then we had the general formula. Maybe I show you the slide that we had at some time. We looked in the random walk and we calculated the second moment of a walker, and so it was n times the variance plus the correlation sum. And now we can plug this in here. So in the last, hope you're not confused if I put here papers in and out of the video. So like we saw, the mean is 0, but the second variance, the second moment is 1. Yeah. So this means the second moment of the walker goes n times, so here let's write it down, the second moment of the increments plus now the sum of all increments ei times ej, where I is not equal j, and that's the correlation sum. And so this here is 1. And now we have to, in order to find out what our second moment, so the mean square displacement of the walker, is doing, we have to figure out here the correlation sum. And so it's a double sum. We sum over all indices I and all indices j, but the only thing we leave out is if I equals j. Okay, maybe so let's write down this double sum. So we have n plus, and then we have a sum. So we have the index I, which goes from 1 to n, because we want to know the whole thing after n time steps. and then now we sum over all j's, and j goes from minus n with plus n, but j should not be equal to I, and then we have this ei times ej. But what we want, we would like to plug in our autocovariance functions, which we know already, which is something similar, but here we need the time difference between I and j. So let's make a variable transform for the j, so that we have here the time difference. And this means, so we write this equals n plus, so we have here the sum I equals 1 to n, and now we sum, and the sum, now we have the time difference. The time difference goes from p equals minus n minus e until p equals n minus e, and the time difference should not be 0, and then we have the increment ei times ei plus p. Yeah, and this is now the variable transform. And here then we have our autocorrelation function c of p that we can plug in here. And so let's rewrite this again. So it's n plus, we have here the sum e equals 1 until n, and you see here we have a symmetric thing, either we go in the future or in the past, but this is always the same. So let's just write a factor 2 in front of everything, but then sum only in the future. So we sum from p equal 1 to n minus 1 our correlation function. And so you see already, so in order to get the second moment of the walker, we have to sum up correlation functions here. And so this is now the sum here, our alpha to k. And at this moment, so here so that's basically a very general formula. So this works, what I did now, this works for all walks, so that's correct in general. But in order to proceed, we need to simplify this here. So that's okay. Maybe let's write this like this first, because that's our result. The second moment as a function of n is just this formula. So the second moment increases with n, and that was usually the diffusive behavior. The second moment increases with time, and then it increases with this sum over all these autocovariance functions. And now there comes a cool trick here, and the trick goes like this. So let's assume this c is a function which decays very fast, yeah, and then we can replace this sum, so we make an approximation, n plus 2 times, we have the sum I equals 1 to n, that's the same. We have here the sum of our correlation functions, and now we have p equal 1, and then we don't sum up to n minus 1, but we sum up to infinity. So we make an oh geez, sorry, went out of the, so like, yeah, so we that was all the same. We sum up from p equal 1, but not to n minus 1, but to infinity. So we make an error, but this error depends on all the terms which are all p values which are larger than n minus I, and but if this is an exponential function, yeah, so we have here additional terms which hopefully will not make a strong contribution because they decay very fast. Yeah? So we replace the finite sum by an infinite sum, hoping that the contributions here for large time distances can be neglected. Of course, this works only. We can do this here only if for large time. Difference, yeah. So this meaning this n, also for large times, this n must be large enough so that we have here values large enough so that all the major contributions of the autocovariance functions we have already. Yeah. And now the trick is, like when we can do this, you see here on the right side we don't have the index I anymore, so we can so we sum over all i's, but something which doesn't depend on I, so we can write this as n plus 2 times n, because the sum we don't need, it's replaced by a factor n, by this sum p equal 1 to infinity over the autocovariance function. Yeah? And so now we see we have when we have our autocovariance function, yeah, so we need basically to sum all values in the autocovariance function. Yeah? So we sum over all of this, yeah, and then we get here this contribution. But basically you also see we are in a diffusive behavior, because the second moment as a function of n now can be written as 1 plus this correlation sum p equal 1 to infinity over this times n. Which basically means this is diffusive again, because when you work out the sum and when the sum converges, in this case of course it might diverge, but if this converges, then we have here behavior where the second moment, mean square displacement, increases linear with time, so we have diffusion. And so this trick here to replace the finite sum here by an infinite, that's Taylor's trick. Where should I write this? That is the Taylor trick. Yeah. And so that's also sometimes called the Taylor formula. And okay, now we can so that's again very general. This goes for very general autocovariance functions, yeah, which decay. I mean, the important thing is that the covariance functions decay fast enough that by this Taylor trick we don't do a strong error. Yeah. So this means for all short-term memory processes we can use Taylor trick, and then we have this formula. Okay, now let's calculate this for our example, because we know the c of p, that's our exponential function. And so basically what we have to do, we have to calculate let's write this here. Let's first calculate the sum. we should calculate the sum of our C of P from P equal 1 to infinity. So that's the sum of alpha to K from P equal 1 to infinity. So that's nearly a geometric series, but in a geometric series we would start from 0. But that's no problem, so we can rewrite this as a function, the sum where we start from 0. So it's again one of the standard tricks of alpha to K, and then we need to subtract 1 again. Yeah? And now we know this here. This is a geometric series, so this is equal to 1 over 1 minus alpha. So this means the whole thing can be written as 1 over 1 minus alpha minus 1. So we inserted here the geometric series. And this is alpha over 1 minus alpha. So that was the correlation sum in here, which so that was here the sum over the C of P, and this we can plug in here in this formula here in the bottom. And then we find that so the second moment as a function of time is 1 plus alpha over 1 minus alpha times n, and this is 1 plus alpha over 1 minus alpha n. So what we find is diffusive behavior. Yeah. So we have again diffusive because the second moment goes as a square root of n, and we can also and this combination here, that's the diffusion constant. Let's look at the diffusion constant. So we can make a plot. Let's have here all possible alpha ranges. We've seen this alpha goes between -1 and 1. Here's 0. And now we can plot this function as a function of alpha. And for alpha equals 0, we go to 1. For alpha equals 1, we have here a pole. And then we have function which increases it's here for -1. If alpha equals -1, we're 0. Sorry, so it goes here from 0. Maybe I make this in color so right. So we start here from 0. This means so like if we have a diffusion constant which changes with the with this parameter alpha, and this alpha was depending on our q. So and if q equals 0, this means alpha is -1. This totally anti-correlated walk, so the mean square displacement is 0. So basically we don't have diffusion, and this we see here in this figure. If alpha is -1, so q equals 0, so the walker doesn't proceed at all. For alpha equals 0, meaning q equal 0.5, we have our normal diffusion constant. And if alpha it goes to the limit of alpha equal 1, our diffusion constant goes to infinity. This means in this case here q equal 1, I mean we approach this ballistic movement, and so like we have very strong diffusion constant. But now there is a puzzle. Remember, I said in the beginning, when we started with this process, we made some educated guess what would be the mean square displacement. And for q equal 0.5, I mean this was corresponding to alpha 0, we had our normal diffusion. But here we say, here we go with 1, slope 1, and here we go with slope 0. But what we found out now is that we should always go here, the second moment should go linear in time. This means the square root of this should go with the square root of time, which means in a log plot we should always have here, for all q values, we should have functions which increase here with the slope 0.5. Yeah. But how is this possible? How can it be that we got this analytic formula which says we should always have such a slope, but in the limiting cases we have these and this blue line? And now the trick is that the solution is that in order to calculate this, we needed Taylor's trick. And Taylor's trick, so this where we added new terms in the correlation sum, this works only for long enough time difference, because only then we can forget about all the extra terms. This means the diffusive behavior that we have seen here in this example works only if time is long enough. This means the real trajectory is like this. For example, if we have this line here, so we start first with something which is not diffusive, which has a slope which is larger than 1/2, and then the slope after a certain time goes to this behavior. So in the long time we're diffusive. Now then this would be, for example, the case for q equal 0.6. Now let's say what's happening for q equal 0.8. So we start with something which is beginning like a ballistic movement, but after a certain time we see a transition, and after this time window we have again diffusion. Now we take q equal 0.9, again we start ballistic, and after a longer time we go to the diffusive behavior. And why do we need to wait so long? Yeah, that's we have seen here in this example for a q nearly 1. So we have long series of ballistic movement where the walker goes in a straight line, but eventually there is a turnover, it goes down again and then it goes up again. If we then wait long enough, then we see an average this is again diffusive. But on a short time scale it's ballistic. So we really see on a short time the mean square displacement goes ballistic, and then we have a crossover to diffusive behavior. And if we wait long enough, we always are diffusive. Similar in the anti-correlated walk. In the anti-correlated walk also we start to go, we don't see anything at all, no movement, but after a certain time we have diffusion. And if q goes smaller, stronger anti-correlation, it takes longer until we go to the diffusive, we go over to the diffusive behavior. So q equal 0.4 and so on and so forth. So you see, after a long time we obtain a diffusive behavior. So this means like when we have a short-term memory in the process, And that's the shortest possible thing we can do, because the next step just depends on the previous step. But then with higher orders it depends also on the step before and so on. So we have a memory which then exponentially decays in time. Means for short term the memory is really clearly visible, and the mean square displacement deviates from a diffusive behavior. But we wait long enough, and then you see, independent of the parameter q, the walker always goes with mean square displacement with the slope 1/2. So this means after a long time we are always in the same universality class, and we still have diffusion. And if you now want to know what's the time scale that we need in order to go to the diffusion, we just have to wait until the correlations have decayed here. So you just see from this exponential function, so you get a typical time scale, which is in this case here just some iterations, but it depends of course on the alpha, on the diffusion constant, as we have seen, how long you have to wait until the correlations have decayed, and we go over to diffusion. So I thought this would be an interesting example, in particular if we compare this example to the example before, where we had no memory but a bias here, but in both cases we always ended up in a diffusive walk. And then the question is, are there more interesting examples where we go out of the class of diffusive behaviors? And these are the more interesting examples we're looking for in the lecture here, and so we will look at these in the next videos. For the moment, thank you.